This presentation will follow section 13 in your workbook entitled More on Arrays and Pointers and Pointer Arithmetic. The presentation will be divided into two parts. This is part one of two. The presentation will cover two main topics: the differences and similarities between arrays and pointers. A lot of that will be review, but there will be new material as we go. And we'll close this presentation with an introduction to pointer arithmetic. So to begin with, the name of an array is like a pointer, but furthermore, it's more like a constant pointer, meaning that you can't change where it points to. In the example, we have an array A declared with 3 integers. The line A equals address of I tries to change what A is pointing to. That will cause a compiler error because the address A is storing cannot be changed. So that's one difference between an array and a pointer, that an array is more like a const pointer. And we'll see another difference shortly. But first, we'll see a similarity between arrays and pointers. This example shows how you can use dereference on the name of an array to access the first element, just like with a regular pointer. So the two print statements are equivalent. The first printf outputs dereference A or star A, which will print the first element in A, which is 4. And equivalently, you can also access the first element using square brackets, as in the second print statement. So A square bracket 0 square bracket. Those will both get the value at the beginning address of the array. An important difference between arrays and pointers can best be seen using a memory diagram. So to that end, we'll consider this example a short function which has one array A and one pointer B. And B is assigned to point to the beginning of the array A. That's the statement B equals A, which could also be written B equals the address of A0. And we're asked to draw a memory diagram at point 1. So if you feel up to it, please take a moment and try to draw your version of the memory diagram now. Here is my version, and notice I've labeled the memory addresses as well as used arrows. Because I was using an arrow, I didn't have to write the addresses, but I added those for your benefit. Similarly, the heap has no memory being used, so you don't need to include the heap in this diagram. There are, however, 2 string literals in the static area. So the difference here is that although star A and star B will both print 4, A itself doesn't have memory reserved just for storing the address. It only has memory for the elements of the array, whereas B actually does reserve 8 bytes to store an address. So put in another way, it would not be correct to have A as a pointer and then drawing an arrow from A to the start of those elements. A itself doesn't reserve memory for storing the address. Here's an example of the incorrect way, and this is how some of the diagrams are drawn in the solutions in double quotation marks. So be careful not to make this mistake. In this diagram, we have A actually as a pointer pointing to the 6 elements. That would mean that A reserves 8 bytes to store an address, which it does not. So that is incorrect. So following along in the book, we're on section 13.4, and you're asked to determine what the output is in this example for each statement, which is using different ways to index an array. And this gets into the topic of pointer arithmetic. So because we haven't covered that, I'll do the first one with you and then try to finish all the other ones. So to begin, notice that B is pointing to the array A. The statement B equals A makes B point to A. And the first print statement prints an integer, and it's given the argument star in parentheses b plus 3. So this is using the idea of pointer arithmetic. The plus 3 will move where b points to 3 elements ahead. So b is currently pointing to the start of a, which stores 4, and then b plus 1 would be pointing to 2, b plus 2 would be pointing to 3, and b plus 3 is now pointing to the 1. So b plus 3 is the address of that 1, and then star b plus 3 gets the value there, which is 1. So now go ahead and try to guess what the values for the other print statements are, and consider the address of A to be 800. Alright, now welcome back, and here's the solutions. So we'll go through one by one. The second statement is printing an address. You can see the %p indicates that it's a pointer, and the argument is a plus 2. So using the idea of pointer arithmetic, it will advance where a points to by 2 elements. So a is currently pointing to the start, which is the address 800, which has the value 4. A plus 2 will advance it to 808, which is where the value 3 is being stored. But we're printing the address, so we see 808 in that case. Next we print the dereference of a plus 1, which prints 2. A good thing to note at this point is that the plus 1 doesn't mean increase the address by 1, so a plus 1 doesn't equal 801. It's smart enough to know how far to advance to get to the next element. So it's storing ints, so a plus 1 goes from 800 to 804 because it knows that an int has a size of 4. The next output simply prints 800, which is where a is being stored. The following output, star a plus 2, will evaluate first star a, which is the value at the address a is storing, which is a 4, and then plus 2. So that one gets to the operator precedence that star a happens before the addition. That's why if you forget the parentheses, you might have unexpected results. Okay, the next example we have star of a plus 1. So this one has the parentheses, so it moves the pointer to point to the second element, which is a 2. And lastly, B is pointing to A, and you can actually use array index notation to get to the second element of A using B by writing B in square brackets 1, as if it was an array. So we've seen before that you can declare a pointer as a function argument using the star or the square brackets. And this gives some examples of equivalent function prototypes. If you compare the first two, you'll see int x with 10 inside square brackets and then x with just empty square brackets. Those are equivalent, and it's actually bad style to include a specific size because that size just gets ignored as a function argument. And if you compare the second with the third one, those are directly equivalent. Based on what you've seen before, where you initialize an array, that gets treated as a constant pointer. But if you pass it as a function argument and declare it like int x square brackets, that's just a regular pointer. It's not a constant pointer, and it's allowed to be changed. And it's the same thing for different types. So in the fun 2, we have character pointers. Next is section 13.6, which just shortly reiterates the difference between initialization, where you declare a variable and assign it at the same time. Assignment happens after you declare the variable. When you work with arrays, there's a variety of ways to initialize them. The first line, we're just declaring an array, and it would be assigned values later. The second line initializes the first three elements of my array 1 to be 2, 5, 7. Although it allocates space for 6 integers, it only initializes the first three. So in a memory diagram, the last three would have question marks inside of them. The next statement, my array 3 with empty square brackets, will automatically adjust the size to have just enough to fit with what it's initialized with. So in this case, there's 4 integers, so that would make my array 3 have space for 4. And try to think what would happen for the next line. In the next line, we have specified that we're only making space for 3 integers, but we try to initialize with 4. That would most likely cause an error for most compilers. And the same idea with a string or a character array in the next line. String 3 allocates space for 2 characters, but we initialize it with a string of length 4, which actually needs 5 characters because the /0 at the end, the null terminator. The following ones are all okay, and we'll specifically see the difference between, for example, string 2 and string 5, with another example in the next slide. So based on what you know, try to draw a memory diagram for this small program. The first line declares an array of characters and stores the string Jack, and the second line declares a pointer which points to the string Joe. Did you catch the subtle difference? S is declaring an array, so it allocates space on the stack, as you'll see in this memory diagram. The string Jack is stored in a character array that has 5 characters, whereas the pointer to a character, PTR, is just pointing to a string literal that gets stored on the static area. So that's the difference between initializing a character array versus a character pointer. This memory diagram also gives an example of memory alignment. So S0 is using address 800, but because it's a character, the next available address going up in the stack is 799. Remember that memory is arranged in 8-byte sections for 64-bit machines and 4-byte sections for 32-bit machines. In this case, if pointer started at address 799, it wouldn't fit in a single 8-byte block or section of memory or a single 4-byte section of memory on a 32-bit machine. So because of that, I rounded it up to the next available memory aligned address, which is 796 for 32-bit machine or 792 for 64-bit machine. I would accept either answer on an exam. And if you ever notice something that's not a character that starts at an address which is an odd number, that's indicating that there's some sort of problem and you've forgotten about memory alignment. Now in section 13.9, we more formally describe pointer arithmetic. We saw that just a few slides ago when we had, for example, a pointer pointing to an array, and we had that pointer plus 1. That's pointer arithmetic, and instead of increasing the address by 1, it's smart enough to point to the next element, which in the case of integers is actually increasing the address by 4 instead of 1. These 5 bullets are valid pointer arithmetic operations in C or C++. You can have pointer plus integer, which we saw before, but you can also have pointer minus integer, pointer minus pointer, post increment or pre-increment of a pointer, and similarly for decrement. Any other operation is not legal and will cause a compiler error. So for example, integer minus pointer is not allowed. Neither is pointer plus pointer. A nice way to think about what pointer arithmetic does is by looking at that last line. If the pointer points to current address, pointer plus integer gets converted to current address plus n times the size of the type that it's pointing to. So for integers, the size of an int is 4. So pointer plus n gets converted to the current address plus 4 times n. Now let's consider this example and see how pointer arithmetic looks like on activation records. So we have an array of doubles, which has 3 doubles called D, and a pointer that's pointing to the first element of D. And we'll have a memory diagram at point 1, and then we do pointer arithmetic to advance the pointer by 2 elements, and then draw an activation record at point 2. So please take a few moments and try to draw the activation records for both points now. Here we are at point 1, and the pointer has been assigned to point to the first element of the array D. And notice we're having doubles in the array, so the address is increased by 8 as we go down. So now let's see what happens after we do the statement pointer equals pointer plus 2. Here we are at point 2, and pointer advances 2 elements in advance. So now the address that pointer is storing is 816. It's not storing, in particular, 802. So pointer arithmetic is smart enough to know how far to advance to get to the next element. Another type of pointer arithmetic, you can have one pointer minus another pointer. And in this case it will return the number of elements between the 2 pointers. For that operation to make sense, both pointers must be pointing to the same type. If they're not pointing to the same type, that would cause a compiler error. In the example we have pointer PTR, which points to the third element of A. And the difference, pointer minus A, is using pointer arithmetic, so instead of subtracting addresses, it returns the number of elements between the 2. So it would return 2. Section 13.10 gives an example with pointer arithmetic. So let's just start by looking at the functions that we get. The first function is called myStirLen. It takes a string and returns the length of the string. But unlike what we did in class before, this one determines the length of the string using pointer arithmetic. So the last statement in that function, return p minus string, is using pointer arithmetic. The strategy is the same, but instead of having an integer variable that gets plus plus each iteration, we're incrementing a pointer instead. Now take this opportunity to draw a memory diagram for point 1. Here is the result. Hopefully yours looks something similar to this. One thing to note is that although they were constant pointers, it's not required to label const on the diagram. And note that the return value hasn't been sent back to main, so length is still uninitialized and has question marks inside of it. Speaking of return values, although you may not have used it or seen it before, there is no restriction on the type of a return value from a function. So you could return an enum. In lab 1 there was the enum for a count type. That could be a return value. You can also return pointers, as in the second example, a pointer to a double is a return type. As well, you can return structs and pointers to structs. We'll see more about pointers to structs in class and also in lab 3. And that concludes part 1 of 2 for more on arrays and pointers. We covered several similarities and differences between arrays and pointers, and I also introduced the topic of pointer arithmetic. In the coming presentation, we'll talk about arrays of pointers as well as pointer to pointer. Now please try this multiple choice question on the material we just covered.